Hello all, this is a continuing of 5.2 where we're talking about series, and this is more of like the lecture base. The video before this is looking more at activities. By the way, if you need to see any of these things, if you go on Canvas and go into modules, you will find these videos as well as the keys that I go over and some blank ones in instructional materials. Also, another resource that I have posted in there is specifically called Paul's Notes. Paul's Notes right here, and it's just another resource, online textbook, something that I used and has been updated since then. Okay, on to our lesson. So we should be pretty aware of what a sequence is. We just have a list of numbers, that's a sequence. When we actually start to add together that list of numbers, we call that a series. And so this is kind of when we're talking about partial sums. If I add together the 1, 2, 3, 4 first 5 terms right here, that would be my partial sums, and that would be, yeah, P5 right there. So that'd be my partial sums that I would have. So I can actually write it with this summation notation, which says cycle through n equals 0, n equals 1, n equals 2, all the way on to infinity, and add those things up right here. So for example, we can actually change kind of what we call our index. So this n equals 0, that's what we call our index. And if I start out with an n equals 1 and I start plugging that in, this whole term would end up becoming 3 to the first power on the bottom. And then if I plug in 1 here, I would end up having a negative 1 squared, so a positive 1. Plus, actually, maybe not a plus, but we'll see. So when I plug in 2, that's my next term in my series, I would have 9 on the bottom, or 3 squared, and then a negative 1 to the third power, which would end up giving me a negative 1. And I can keep on doing that. And we'll see I actually get the same thing here when I start with 0. So if I subtract 1 minus 1 from my indexing, that means I actually am adding 1 into my exponent. And up here, it doesn't really matter because we just need to make sure that our first term is positive and our second term is negative. So that's how you can kind of change your index. So this is like a general rule of thumb. So with summations, just like when they were introduced in Calc 1 with Riemann sums, we can actually add them together, we can subtract them, and then constants can kind of move in and out as long as the constant doesn't depend on our sequence term, so like our a sub n that we have there. So still kind of those same rules that we're used to. So just like with sequences that had arithmetic sequences and geometric sequences, we can also look at that as opposed to series. So if I were looking at just an arithmetic series, which means I'm adding together terms of my sequence, I could just be adding together 2n, so that's like a linear function from n equals 1 to infinity. Arithmetic series. And I can also have a geometric series, and that would look something like if I had 1/2 raised to the n power. And that 1/2 would be, I think we called that our ratio, that would be our r value. And that again varies from 1 to infinity. Another option for series that we've kind of learned to define is called a telescoping series. So within a telescoping series, that means that things kind of start to cancel out. So like if I look far enough out, hence the telescope, if I look far enough out, all these terms are going to end up canceling out, and I can kind of make up a pattern of what it's going to be. So for example, if I had this as my equation, which we could actually verify is truly equal to these two terms, and I could do that through partial fractions right there. So let this be my a, let this be my b, and actually solve that out. When I have a telescoping series, it is really, really nice to be able to actually write all my things out. So by the time I get down here to my partial sum of k, you can start to see that this was my this was my S1, this was my first sum. Then I added 2 terms, and so these will actually end up canceling out. My negative and positive 1/3 will cancel out, and that'll just keep on happening until we end up with just this term at the end and then the one that we started with. But remember, this is just our kth partial sum, and our series actually goes out towards infinity. So my sum here will actually be the limit as my partial sums approaches infinity. So as k approaches infinity, we take our limit of what we found right here. This whole chunk is actually going to go to 0 because my denominator is growing faster than my numerator, and my partial sum will just end up being 1. Let's look at an example of that. So for example here, easiest way to actually kind of start to write this out is by plugging in our n equals 1, and then we'll plug in 2, we'll plug in 3. So if I plug in 1 here, I'll actually have cosine of 1, so this is my n equals 1 term, minus cosine of, when I plug in 1 here, I'll have 1 over 1 plus 1, so I'll have cosine of 1/2. Okay, now I'm going to plug in n equals 2. So I'm plugging in 2 to the first part, I'll have cosine of 1/2 minus cosine of 1 over, and then 2 plus 1 is 3. And hopefully we've already started to kind of see a pattern emerge right here, but I'm just going to do the third one for fun. I'll have cosine of 1/3 and then minus cosine of 1/4, and then I'm going to skip a few, and I'm actually going to go out to my kth term. So I'm going to say n is equal to k. This will be my partial sums, my kth partial sums. So I'll have cosine of 1 over k minus cosine of 1 over k plus 1. And I'm going to start canceling some things out. So these look like they cancel out, these look like they cancel out. This is going to cancel out with the term right in front of it, and this will cancel out with the term that is right in front of it there. So if I look at this, as my limit of k is approaching infinity, I will actually only end up with my cosine of 1 and then minus my cosine of 1 over k plus 1. The same kind of thing happens is as k approaches infinity, it doesn't actually impact this part, but it does send this to 1 over a huge number, 1 over a huge number. So this inside part will actually approach 0. So I'll end up getting cosine of 1 minus cosine of 0. Well, cosine of 1 is some weird number. I'm just going to leave it as cosine of 1 minus cosine of 0 is just 1. That is what this summation up here will actually, and it ends up being this very, very long decimal. I actually just prefer to write it like this, but this is a good estimate of what it would be. Now you do have some practice problems that you're actually going to be evaluating and turning in as a separate homework assignment. So I wanted to give you a few kind of hints on those. Right here on these first few, I would try to decide what is actually changing and if you can look at a pattern depending on what your term is. So this is my 4th term. How can I compare my 4th term to what is happening into that part of my equation? Also, -1 to the n or -1 to the n plus 1, or it could be any form like this, will probably help you try to figure out how these are alternating back and forth between negative and positive. My other hint is on these next few that I have here. So I already have a hint on this one. On this next one, I'm kind of trying to figure out, so it's helpful to try to write this as a series. And we can kind of see that 10, we're multiplying by 10 each time here. which is kind of equivalent to raising 1/10 to our n power. And then, okay, last hint that I wanted to give is in this very last telescoping one, it might be helpful to remember the rule that when you are dividing by something inside of a log, you can actually rewrite it this way with a subtraction in between. Okay, y'all. Hope you have a beautiful day. Bye.